has to be an increasing value. The one thing that's usually tricky for students is if you had to do this shape. What values of theta should I list for this? See, that's the stipulation. Theta has to be an increasing value. A good many of you have committed this to memory as 3 pi over 2. And you've committed that to memory as pi over 2 in terms of angle location. So if you go from 3 pi over 2 to pi over 2, though, you're decreasing. So you have to kind of think of this as 0 and this is now a negative pi over 2. So to guarantee theta is positive, you'd want to go from negative pi over 2 to positive pi over 2. Okay? Or you could go from 3 pi over 2 to 5 pi over 2. Doesn't matter. As long as it's an increasing direction or an increasing value range for your theta variable, that's the main thing. So, but yeah, since this is the full donut, torus, whatever you want to call it. No, this is actually just a donut. Tori are 3-dimensional. So that's what we actually want to use. R goes from root pi over 2 to pi, and theta goes from 0 to 2 pi. And in most cases, if you're only plugging theta into trig functions, it doesn't matter if you use degrees or radians, but just, just to be consistent in almost every mathematical analytical aspect, theta is always in radians. So just try to adjust, you get used to the radian idea. You had a little bit of exposure to it. Just sort of slide back into radian mode in terms of doing your calculus. So those are our R and theta limits, which means if I set this up correctly as a double integral, the original double integral will be for sine of x squared plus y squared. So let me show you the proper transformation. And on the earlier piece of paper, did you see that I had that denoted as dA instead of dx dy? Sometimes if you're integrating over a 2-dimensional region, sometimes both differentials can be conglomerated into one statement as dA, since your underlying region is a 2-dimensional area. That's what the A stands for. If you're in triple integrals, the first topic for test 4, if your underlying domain is a 3-dimensional volume, the differential can be condensed, and instead of dx dy dz, it can be dv for a 3-dimensional underlying region. But so if you see that dA and it confuses you, just double check with me and I can try to clarify it. But that's really what it stands for. It's either dx dy or dy dx. So that's what we're originally intending to measure, but it's kind of going to be impossible to set the limits in xy coordinates. So here's the way the conversion works. So we've committed to, in almost every case, you can get away with using theta as your outer limits. So 0 to 2 pi will be my theta limits, and root pi over 2 to root pi, as weird as that looks, that's going to be my R limits. The integrand itself, sine of x squared plus y squared, and again, I'm still using my color coding system. Black is rectangular, red is polar, just for this first example. What's that going to become when I convert it into polar? Yeah, sine of any use of x squared and plus y squared, you've got to make that mental connection that becomes r squared when you convert it to polar. Because you're going to see that x squared plus y squared a lot in these polar problems. So you keep the sine function. The sine function doesn't change, but its argument goes to r squared. And then dx dy, this is where you need to remember your integration double integral compensator. The regular dx dy differential rectangular becomes r dr d theta in polar. You always put that extra r in there whenever you make a conversion to polar. It's just part of the process. So dx dy here becomes r dr d theta. And yes, that is an r variable that is intended to be incorporated with this function for integration. You integrate this with respect to r, and then go back and integrate whatever's left for theta. But here's something else that's kind of cool. Look at these limits. Constant limits. Technically, you're integrating over a polar rectangle, because remember when you integrated over a double integral xy rectangle, you could split it up to where you had a function of x here with the x limits times a function of y with the y limits. Can this be factored as a function of r times a function of theta? Be careful. All you see is r's. So technically your function of theta is the number 1, d theta. Yeah. So it can be factored. If you see that you can do that, you can apply the same shortcut here, because one of the coolest things about polar double integrals is when you make the conversion from rectangular to polar, these regions that are circular convert to constants for r's and thetas. If you got constants on the integrand, you can split it up. So since this is factorable, I'm going to use that rectangular double integral shortcut. Kind of redundant to write that 1, but really the only function of theta there is the number 1 d theta. And then times the integral from root pi over 2 to root pi for sine of r squared r dr. Get your pirate jokes out now if you want to. And so what's that going to become? Your integral there would be theta, upper limit 2 pi, lower limit 0, just pops out of 2 pi. Times the integral that you get for your r. Now what you going to need to do here? U sub. You've got a squared r in the trig argument, you got a linear r outside, and conveniently it's already paired with your dr differential. So, sorry about the heinous color coding I'm doing. So if you equal r squared, 2u is, or du is 2r dr. So I'll just fudge a 2 there to go with my r and my dr. That all becomes du. So I'm really integrating half of sine u. And yes, I'm going to change my limits. Because if you got a definite integral and you're committing to a u sub, go ahead and convert the limits, and you don't have to undo u at the end. My conversion is u equals r squared. So the bottom limit pi over 2, root pi over 2 for r becomes what over here for u? Pi over 2. Because you're just going to square that r value and it becomes your lower limit for u. Pi over 2. Upper limit here is root pi. U is that squared, so pi would be your upper limit here. And that becomes negative 1/2 cosine u. Plug in these limits. Didn't really give myself too much room to do this. But again, I'm going to take this answer and multiply by the 2 pi, and that'll be my final answer for the whole thing. Pi plugs in, cosine of pi is negative 1, so that's negative half times negative 1. That gives me a positive half. And then minus negative 1/2 of cosine of pi over 2, which is goose egg. So the only thing this other r integral contributes is just the number 1/2. So I take that back. Evaluates as 1/2. So all this work for that beautiful number. Pi is the value of this function's interval over this concentric circular region. One polar double integral versus the prospect of having to do 4 dy dx integrals if you stuck with using the xy direction. And that would suck. Not only that, can't integrate that bugger. If you left this in terms of x's and y's, there's no linear x or linear y out here to work with the u substitution. So there is no way to take an antiderivative for sine of x squared plus y squared. So, yay polar. In some cases, you know, polar's the only saving grace for a problem. So my main thing that I try to impart to Calculus 3 students is look for these circular regions. If you see domains of your double integrals converting into circular regions or portions of circles, think polar. Also, the liberal use of this x squared plus y squared expression is also a really good visual cue to let you know that you want to convert to polar. Okay? So far, so good? All right. Volume is still a valid context. Determine the volume of the region above the xy plane bounded beneath the paraboloid in the first octant. Now, I'm going to go ahead and assume y'all didn't do too much of the graphing back in the first test with all the oids, the paraboloids. Do you even know what a paraboloid looks like? Just naming it like that.
So?
That's the hyperbolic paraboloid, because it's got hyperbolic cross sections this way and parabola cross sections this way.
Like a cone?
This one is like a bowl. This one actually if it's just z equals x squared plus y squared like this, that's a paraboloid vertex at the origin opening upward. If you put a minus in front of the x squared plus y squared, what transformation would that do to it?
Turns it down.
Opening downward in the z direction, the negative z direction. What's that positive 4 going to do to it? It's a vertical shift, just like in pre-calculus. So this is technically a paraboloid opening downward from the z value 4 over the z-axis, looking something like this. So I'll probably afford you a picture. And it's also isolated just to the first octant. So it looks something like this. Here's my z value 4. It opens downward like a parabola. And then when it meets the xy plane down here, what's the cross section going to look like? Circle, yeah, because you've got that x squared plus y squared expression. If you look at the level curves, if I set this equal to z equals 0, the level curve at z equals 0 would produce x squared plus y squared equals 4, a circle of radius 2. So if I give you this picture, that's what this object looks like. But this is our polar domain down here. And I'm going back to just all black now, just because it's going to get really crazy going back and forth from black to red. Okay, since this is the graph of z equals 4 minus x squared plus y squared, x squared plus y squared, yeah. That means when it meets the xy plane down here, it makes a quarter circle of radius 2. And again, the easiest way to do that is just to set your z in the equation equal to 0, and it generates the rectangular equation x squared plus y squared equals 4, a circle of radius 2, so at the origin. So that's our polar domain. This is the region we're going to integrate over down here. And what becomes my integrand if I'm trying to calculate a volume? What should be integrated if you're doing a double integral over this region?
R times 4 minus r squared.
Well, don't convert it to polar yet. What do I integrate if I want to find the volume between this region and the surface?
X squared plus y squared.
Yeah, the paraboloid is what's on the top of the shape. So remember, volume that we talked about on Tuesday is the double integral over the underlying region R, there's our region R, of the function alluded to in the problem. Okay, dx dy or dy dx. So that's my integrand right there. That's what I'm going to integrate over this quarter circular region in the first octant. Okay, so if I set it up as a rectangular integral without really doing the limits, it would look like this. Double integral over the region R, so I'm keeping that generic because I don't want to ultimately do it in rectangular. I want to convert it to polar. Why polar?
That's a quick question before we move forward. How do we know that that's the only thing that we need to integrate is just that space?
That space, determine the volume of the region above the xy plane, so it's above the xy plane, and it's bounded beneath the paraboloid. So it's under this paraboloid and above the xy plane. Never in your life will you ever have to pay more careful attention to prepositions. Okay? Above the xy plane, beneath the paraboloid. So,
but it's that whole piece right there, right?
Yeah,
it's not just
it's
that
this
little
whole 3D
sliver.
thing. This is the base. This is
Okay.
the contact with the tabletop,
Okay.
and it's the
Thanks.
3D solid from here up to that parabola. So the parabola is the top. And if you were looking at this and you could rotate it around to check out its laterals and stuff like this, it's got a flat face over here on the XZ plane. It's got a flat face over here on the YZ plane. The only curved surface is right here where the paraboloid is. What we're actually seeing here in the first octant projecting toward us. Okay. So yeah, that's the solid we're trying to find the volume of.
I thought for a second that we were just trying for that little sliver there.
No, that'd just be an
That
area.
was all shaded.
Yeah,
That
if
was
you
like-
want to find an area, you can do it with double integrals. You just do the double integral with the function 1. And because that tells you, if you have a height of 1, it's really that area times 1 to give you the volume. So it kind of defaults to also telling you the area of the underlying region. But yeah, as a rectangular integral, we would be integrating the paraboloid's equation because it's what's on top. But then I want to convert this into polar. So, looking at your underlying region R, since you're in the first octant, we're isolating this to the first quadrant. So that shaded region here is essentially this region in the XY plane. What would that represent as your theta limits?
0 to pi over 2.
Theta, 0 to pi over 2 for theta. And drawing r from the origin outward, are you always going to have the same values of r no matter which way you draw that radial ray? From the origin outward, it's always going to start at 0 when you start at the origin, and it's going to contain every r value from 0 all the way to 2 in all directions for 0 to pi over 2 for theta. So r goes from 0 at the origin to 2 at the outer radius, and then we got to convert our integrand. 4 minus x squared plus y squared becomes what?
X squared plus y squared equals 4.
No. Convert it to polar.
R squared.
Yeah, 4 stays 4 for now. X squared plus y squared becomes r squared for now. But then, now that we're officially converting to polar, don't forget, there's an extra r, and then dr and d theta. So that's why you want to pay careful attention to the literal use of that x squared plus y squared in so many of these polar problems. That's a direct polar counterpart. So paraboloids work really well with polar coordinates because every paraboloid is going to have some kind of x squared plus y squared in its equation. And that converts pretty easy as your integrand. So really, go ahead and multiply this out. Don't leave it like this because you'll make the mistake of integrating factor by factor, but you got to integrate term by term. Turn this into the integral from for 4r minus r cubed. And then you can split this one up if you want to. A good many of them can, because if you don't have any functions of theta in here except for the d theta, you can always go back and do what I did there in that first example if you want. If that breaks your heart and you think you're jipping theta for some reason, you can always just go one variable at a time. Just integrate r first, and that gives you 2r squared minus 1/4 r to the 4th. So the integration is no different. You still use the same antiderivative rules. Nothing calculus-wise is different except for this extra r with your differentials, and then the calculus proper of doing your integration is still the same rules. So 2 plugs in, you're going to get 8 less 4, which is 4. And then when you integrate this with respect to theta, now you're switching variables. So the antiderivative of 4 would become 4 theta with the limits 0 to pi over 2. So in this case, and of course 0 wipes that out, so you're left with just 2 pi. And that does represent that full volume. Now this is something you could have done with calculus 2. You could have gone back to calculus 2, assuming you had a very enjoyable experience in calculus 2. You could have taken, oh, that is purple. You could have taken the function, well, one version of it is this. Y equals the square root of 4 minus, no, poo, it's not. I gotta make sure I'm doing this right. X squared plus y squared is solid for that. So this is the equation, this equals 5. Yeah, let's do this. 4 minus x squared, which will produce kind of a cross section that looks just like this parabola. Revolve that from 0 to 2 about the y-axis, and it produces a revolution solid. And you could use the disk method or even the shell method and get the volume using Calc3 logic. Because most of these oids, your cones, your paraboloids, they can be turned into revolution solids and their volumes found with Calc3 methods. The only tricky part is if you do something funky to the domain, like if you cut it by 1/4, you take your revolution solid here and you're forced to go all the way around. So once you got your shell method volume or your disk method volume here, what should you do to your answer?
Divide by 4.
Divide by 4. And then that restricts it to the first octant portion that we saw right here. Okay. Keep trucking. Do you have any questions? So here's one where it's given to you as an xy integral using xy coordinates, and you're asked to convert it to polar and then evaluate it. Would it be much of a bugger to evaluate this as it is? Well, I mean, if you consider, it's got variables here, so it's like one of the ones we did on Tuesday night, where if you wanted to reverse the order of integration, you have to graph and switch to doing x first and then y last. If I integrated y first, xy, not so bad, half y squared, not so bad, but then you plug these roots in. You get x times that minus x times negative that, so that wouldn't vanish. But then for half y squared, the root plugs into both of those, they're both the same sign. When you subtract them, that part would go away, and you're left with 2x times one of those radicals. And so you could do it with a u sub, but let's just see what happens if you convert it to polar, all right? One thing you're going to want to, I guess, also develop your visual acuity to recognize is this circle equation, x squared plus y squared equals 4. That is a full circle of radius 2, centered at the origin, looking something like this. Versus, if you take one of these equations like this and solve it for y, that requires you to subtract the x squared from the 4, so that gives you y squared equals 4 minus x squared. There's the expression in a radical. But notice you got to take the square root. Whenever you algebraically take a square root, you have a plus or minus that's involved on that root of 4 minus x squared. So in the process of solving this circle's equation for y, you could solve it and get the positive square root, which would give you, well, what part of the circle?
The upper half.
The upper half. So there's the y equals positive square root half. And then the lower half comes from the y equals negative square root half. So another visual cue, sorry for the shorthand notation, but I think you see what I mean. Plus or minus square root here generates the top and the bottom half of those circles. Both of those are equations are used right here. So in order for me to convert this to polar, I need to graph this region using xy coordinates, just so I can see exactly what the shape is. Is that going to give us this full circle? Yes. Maybe. Well, let's double check, okay? According to what we did Tuesday night, the inner limits pair with dy, so that means our y direction, y goes from the negative square root of 4 minus x squared to the positive square root of 4 minus x squared. Okay? So just this alone, well, is this. Y equals negative root 4 minus x squared to positive in the y direction first. You'll always have a consistent y entrance and y exit with those two semicircle equations on the bottom half and the top half. But then cross that with the x coordinates. The x direction, or the x components for the integration, x is restricted from going to 0 to 2. So, if I do the y direction first, and then if it's flattened to the x-axis, it only gives me that interval.
First and fourth quadrant.
So it's the first and fourth quadrant, the right half of this circle, all because of those x limits. See, if you just trust the y limits alone, the y limits give you both circles altogether. But you got to make sure you cross-reference them with your x limits. X only goes from 0 to 2. So really that means our region looks something like this. See, this is still the lower half of that circle. This is still the upper half of that circle. So that would still be y equals negative root. And this is y equals positive root. But then x goes from 0 to 2. Well, I mean, what would have to be the x values if you needed the full circle? The x values here would have to be what? Negative 2 to 2. And since you're kind of cutting it in half, you're only using the right half of that circle of radius 2 centered at the origin. So does this lend itself to polar? Sure. If you see any circular attribute to your domain whatsoever, I would jump like a good lemming right off that cliff into polar. Okay? So, according to polar logic, R goes from... Now again, when you're drawing your R, you have to draw it into the shape itself. You don't want to draw R over here, because there's no part of the solid that's to the left in the second or the third quadrant. So if I draw any ray from the origin outward into this shape, am I always going to have the same limits for R? Starts at the origin where R equals 0 and ends at the radius of the circle where R equals 2. And then what theta values span this shape?
Negative pi over 2 to 2.
Yeah, because you're in the first and the fourth quadrant, you don't want to make the mistake of calling this 3 pi over 2 and then calling this pi over 2. you're actually causing your theta to decrease. Theta needs to be in an increasing orientation. So you want to think of this as negative pi over 2, and this is pi over 2 for this particular kind of shape. But again, any coterminal angles with these two, so long as it's still increasing. I mentioned earlier, calling this 3 pi over 2 is fine, so long as you call that 4 pi over 2 and then 5 pi over 2. Okay? As long as it's increasing, it's fine. It'll still give you the same value. Now our integrand, we've got our limits figured out. So when I convert everything into polar, unfortunately, this is the first integrand that doesn't have x squared plus y squared in it. And no, you can't just arbitrarily make it x squared plus y squared just because you want it to. Okay, the original integrand is fixed as x plus y. X can only be replaced legally with what? R cosine theta. Don't forget, there's 2 parts required. If you have x and y used individually, without the x squared plus y squared combination, you can replace x with r cosine theta and separately y with r sine theta. Okay? It'd be handy to give you this on the test, wouldn't it? Mm-hmm. No problem. Done. So feel free to use those liberally as you're doing the homework. I mean, some of you already have them committed to memory. So we've already got our limits figured out. Theta goes from negative pi over 2 to pi over 2. R goes from 0 to 2. And then one at a time, just make your, unfortunately, I kind of think of those as the lame polar replacements. I mean, they work every time, but I really love to see that x squared plus y squared. And you want it so bad, but you just can't make it happen. So you're faced with replacing x with r cosine theta, and then plus y with plus r sine theta. And don't forget, you might want to put a pair of parentheses around this because what has to also be included here? The extra r that you put in there is a multiplied factor. So you want to kind of preserve the parentheses there because later on you might want to distribute this r through and then, choose your order of integration if you want to. Well, actually, I may factor this one. R limits, theta limits are constants. If you have constant limits and this is factorable, function of r, function of theta, what's your function of r if you split it up that way?
R squared.
R squared. Pull the r out of this as a GCF, and you can have a standalone function of r as r squared, integrated from 0 to 2. And then what's your function of theta?
Cosine theta plus sine theta.
Cosine theta plus sine theta. So you can separate this in terms of 2 single integrals, one focusing on r, one focusing on theta. Okay.
And theta is the outside, R is the inside.
So yeah, in either order, because when it's factorable, you're just separating them apart.
Then you're at negative pi.
Are you doing math in your head?
Yes, sir.
Okay. But yeah, you factor the r out, so I'm going to focus my 0 to 2 on r squared dr, and then times my theta integral, negative half pi to positive half pi for cosine plus sine. So let me pause for a second, make sure everybody sees how that's legal, and don't think I'm doing Hogwarts math up here. I'll do this for Paul. So factor the r is separable, constant limits, we're good to go. That's going to become 1/3 r cubed. So let's go on and make that an 8/3. True? Right? I'm not skipping too many steps, am I? Right? Because that one's pretty straightforward. This one I won't skip any steps on because trig functions make me nervous sometimes. So sine theta minus cosine theta is my antiderivative. The handy thing about cosine in any pi over 2 multiple, well, any odd pi over 2 multiple, is cosine wipes out there. So my sine at pi over 2 is 1. Cosine at pi over 2 is 0. Sine of negative pi over 2, since that's at the south end, your y coordinates are -1 there. So it doesn't vanish. You're tempted to say it's going to go to 0, but no. The theta part of the integral ultimately contributes a 2. A 2 that gets multiplied way over there by the 8/3. To give you 16/3 as your final value. Any questions so far? I want to see if you can try this last one. And since you are given the reference, if you need it, there's your rectangular polar conversions. No pressure. I mean, I'm not going to grade you. I'm just sort of putting you in a kind of do your own sort of work kind of situation while we have a contact hour together. And remember, that dA means it's originally given in XY form. So, well, obviously it mentions X's and Y's in the function, so. Convert that double integral. After you convert the integral, before you evaluate it, let me see what you got. If you raise your hand, I'll come see what you got. That's it, good deal. Oh, yeah?
Is it 50 times 5 or 6?
Oh, I hadn't evaluated it yet, I don't know. I was just asking you to set up the double integral, what it would look like. I don't think it's that big. No, you should end up squaring some pi's when if you do this one correctly. Yeah. You should have some crazy pi squared answers. If you make the conversion pretty, correctly, it turns into a pretty easy integral.
That's what I was thinking.
And then what happens if this is applied to that? Yeah, because they're inverses.
Yeah,
Then you got the extra R.
So
So it's
yeah.
if you convert this correctly, your double integral should be for the function r theta, dr d theta.
Yeah.
Because tucked into this right here, if you solve this for theta, what function do you have to apply to both sides? In other words, to get theta by itself here, I would need to take
The
the
inverse,
inverse
tan
tangent
versus
of the left
tan.
and the inverse tangent of the right. Another name, a synonym for inverse tangent is that arctan. So that's the same thing as inverse tangent. If you solve that for theta, theta equals inverse tangent of y over x. So that means if I converted that integrand to polar, that goes directly to being double integral of theta, because that's exactly what arctan of y over x is. The dA part is what becomes my r dr d theta. Okay. So the integrand turns out pretty straightforward if you kind of caught that little tricky little thing about solving the tangent equation for theta. Your limits are pretty straightforward. R, because this is sort of a circular sector, R goes from 0 to 10 in any radial direction there. And then theta spans from pi over 6 to pi over 3. And since this is constant limits, and that's definitely function of theta times function of R, I can factor it. I'll